Welcome back. We will discuss geometrical isomerism. Geometrical isomerism are exhibited by compounds which are having restricted rotation. It can be due to double bonds, presence of double bonds. Double bonds C, that is carbon-carbon double bond, carbon-nitrogen double bond, or either nitrogen-nitrogen double bond. Apart from that, substituted cyclic compounds can also exhibit geometrical isomerism. Just like cyclohexane, cyclopropane, which are substituted, they can exhibit geometrical isomerism. So why these compounds exhibit geometrical isomerism? Because due to restricted free rotation, geometrical isomerism are exhibited. That is a configurational isomer. Geometrical isomers are configurational isomer. They will be having a specific spatial arrangement. And due to that specific spatial arrangement, they will be differing, those geometrical isomers will be differing in the physical properties and some of the chemical properties also. And we will discuss today the geometrical isomerism of compounds which is having carbon-carbon double bond. Let us go to detail in those compounds having carbon-carbon double bond. So when we take a molecule which consists of carbon-carbon double bond, we know that the carbon is in the sp3 hybridization. So the sp3 hybridized orbital will be forming the 3 sigma bond on one plane, and similarly here also sigma bond on the plane itself. So we can represent it in a plane. The 3 bond sigma bond will be on the plane, and the pi bond will be by the unhybridized orbital, p orbital. Unhybridized p orbitals are there, and this pi bond will be in between this molecule. So the sigma bond are in one plane, and the pi bond locks the molecule above and below the plane. So that restrict free rotation along carbon-carbon double bond. So that's why this type of molecules will exhibit geometrical isomerism. That is, the sp2 hybridized orbital will be forming sigma bonds, and unhybridized p orbital will be forming pi bond. The pi orbitals, that is pi bond obtained by the overlap of unhybridized p orbital, locks the molecules above and below the plane, which will give a restriction along rotation of carbon-carbon double bond. Okay, so which type of molecules, that is carbon-carbon, if all the molecule having carbon-carbon double bond won't exhibit geometrical isomerism, that is a molecule just like this won't exhibit geometrical isomerism. Those molecules which are having different substituent on the carbon, that is ABC, the ACN type, or it can be AB, DB type, or it can be ABC, DE type. These type of molecules will be exhibiting geometrical isomerism. Okay, so geometrical isomerism is exhibited due to restricted free rotation along the carbon-carbon double bond. Okay. How will you name geometrical isomers? Normally, if the geometrical isomers have identical molecules just like ABC type molecule, we used to represent it as cis or trans isomer. That means if two groups are identical, the identical group are on the same side, we call this as a cis isomer. Here, this is a cis isomer. That means the identical groups are on the same side of the double bond. Whereas in this case, the identical groups are on the opposite side of the double bond. So at that case, we call it as or name it as trans isomer. This cis-trans nomenclature is possible only if they have identical or similar atoms, just like ABC, ABC type. Okay, so if all the substituents are different, all the 4 groups are different, we use EZ nomenclature. In the case of EZ nomenclature, we normally prioritize the group. We prioritize the group. If the higher priority groups are on the same side, we call it as Z isomer, and higher priority groups are opposite side, we call it as a E isomer. How will you prioritize? We will giving higher priority to those substituent which is having higher atomic number. So when we come to this example, we know that when we compare to chlorine and bromine, which is having higher priority is for bromine. And here in this carbon, higher priority is for iodine. So the higher priority groups are on opposite side. So we name it as E isomer. It is the E isomer. Whereas in this case, the higher priority group, that is bromine and iodine, are the higher priority group. These are on the same side of the double bond, then we call it as Z isomer. So these are the general nomenclatures of geometrical isomers. Either it can be named as cis or trans or E or Z. Okay. Let us discuss geometrical isomerism in But-2-ene. I already explained that the geometrical isomers will be exhibiting different physical properties, and some of the chemical properties all will be different. So when we take But-2-ene, let us discuss what are the difference between cis and trans butene. So what is the difference between the cis But-2-ene and trans But-2-ene? Let us take the stability of the molecule. Which will be more stable, whether the cis form or the trans form? When we take the cis form, we know that the CH3 group are the bulky groups. They are on the same side. So when they are on the same side, obviously they experience a steric repulsion. So this molecule, that is the cis form, will be less stable than trans form. Cis form will be less stable than trans form. Why it is less stable? Because the bulky CH3 groups are on the same side, and there will be steric hindrance or steric repulsion that destabilize the cis form, and trans form will be more stable. Okay, so when we come about the dipole moment and the symmetry of molecule, here we can see that the dipole will be cancelled in the case of trans isomer. The trans isomer will be having 0 dipole moment, whereas in the case of cis, it is 0.33 dB. Because in the case of cis isomer, there is dipole experienced here. Okay, so due to this unsymmetrical nature of this cis isomer, the packing will be less efficient, whereas trans form can be more regularly packed in the crystal lattice. What gives difference? If there is the difference in the packing in the crystal lattice, the melting point will be higher for the trans form. The melting point will be 167 Kelvin for the trans form, whereas for the cis form it is 134 Kelvin. Because in the case of trans form it is symmetrical, whereas in the case of cis form it is less symmetrical. Okay, Then what about the boiling point? As they exhibit dipole moment, that means they will show polarity. When there is polarity, the interaction between the molecule will be more. And the boiling point will be higher for cis isomer when we compare to trans. It is 277 Kelvin and this is 274 Kelvin. So the cis and trans form of but-2-ene differ in the properties, in the stability, in the melting point, in the boiling point, in the dipole moment, etc. So this is the difference between cis but-2-ene and trans but-2-ene. Okay, let us consider another molecule, that is but-2-ene-1,4-dioic acid. This also exhibits geometrical isomerism. Normally, there will be two COH group, carboxylic group. When these two COH group are on the same side, we call it as cis, that is maleic acid. Whereas the two COH group are on the opposite side of the double bond, we call it as trans form, or it is fumaric acid. These two differ in the property. The stability itself, which will be more stable, the stability will be more for the fumaric acid than maleic acid. Why? Because in this maleic acid, the two COH group on the same side, so they experience steric repulsion due to steric crowding. So this will be less stable than fumaric acid. Maleic acid will be that the cis form will be less stable than the trans form. Okay. So then when we come to the melting point, the symmetry, this is less symmetrical, so the packing is less efficient. So the packing is less efficient, that means in the crystal lattice they are not closely packed. So the melting point of this cis form, that is maleic acid, will be, the melting point of maleic acid is 408 Kelvin. Whereas the trans form are having symmetrical geometry. So it can be closely packed in the crystal lattice. So it has a melting point about 503 Kelvin. So this much difference in the melting point of maleic acid and fumaric acid, as the bulky groups are in the same side in cis, and in the trans they are in opposite side, they are more symmetrical. And obviously here in the trans form, what will be less? The dipole moment will be less, because it will be mutually cancelled each other in the opposite direction. Whereas in the case of cis, they are on the same direction, so they will be more polar. When polarity increases, the solubility in water also increases. That is, like dissolves like. So there is a difference in the solubility. When we take cis form, the solubility is 790 gram per liter for the cis isomer, that is maleic acid. Whereas when we take the trans form, the polarity is least, so the solubility will be less. It is approximately 7 gram per liter. So they differ in the solubility in water. Water is a polar solvent. When polarity increases, like dissolves like. Okay. So apart from that, we can distinguish them by ease of cyclization also. When we take maleic acid on heating about 523 Kelvin, water molecule is eliminated and we will be getting an anhydride, maleic anhydride. Maleic anhydride is formed. Whereas the fumaric acid also undergoes cyclization. But it won't give fumaric anhydride, it will be giving, again, the product is maleic anhydride itself. The temperature should be 503 Kelvin. So at 503 Kelvin, it eliminates water and forms maleic anhydride itself. So we can distinguish maleic acid and fumaric acid from its ease of cyclization. Apart from that, both are acid, which will be more acidic. In this case, we can see that when one H plus is released, we will be getting a carboxylate anion like this, minus double bond OH, HH. This carboxylate anion can be, so in this case, we can see that when one H plus is released, we will be getting such a carboxylate anion, and there is a stabilization due to hydrogen bond in the case of maleic acid. Whereas in the case of fumaric acid, no such stabilization is possible because they are on the opposite side. As they are on the opposite side of the double bond, there is no such hydrogen bonding. So normally here the pKa value is approximately 3, whereas here the pKa value is 1.9. Lower the pKa value, more acidic it may be. So like this, the cis and trans isomers may differ in their properties. And by using these properties, we can distinguish cis and trans isomer, or geometrical isomers can be distinguished by using different properties just like dipole moment, melting point, ease of cyclization, solubility in water, like that. So this is about geometrical isomers of But-2-ene and But-2-ene-1,4-dioic acid. Okay, thank you.